Okay, in case I don't finish all of this lesson, I'm going to do this part recorded. Starting example 3, we were testing symmetry with respect to the x-axis. And, let's see, and the y-axis. So it's both axes are being looked at. Reminder that, let me just give you an example. Symmetry to the y-axis would look like something like that. In other words, it's reflected on this axis right here, okay? Which implies that if you plug in an x value, you'll end up getting a particular y value. You plug in the opposite of this x value, you get the same y value. So all you're really doing is seeing that if you plug in a negative x value in this, will I get the exact same y? You would know it if we come up with the same equation. So if I negative x squared, that becomes y equals, it still becomes positive x squared plus 4, and you'll see that these two are identical. So this was symmetry on the y-axis. Yes, okay. Now to check for the x-axis, let me give you a little reminder of what that meant. It meant that if you have a picture going up like that, and there's a mirror image under on the across the x-axis, if you plug in a particular y value, I could say a particular y value, I'm calling it y1, that this x value corresponds to another y value. I'll call that y2. So you have two different y values if you plug in the same x. So actually that y value is the opposite. I should say that y1, let me call this the opposite of y1. Opposite of y1. I just should erase that so we can see it clear. If that's y1, then this would be the opposite of y1. So why don't we do the exact same trick? I have y equals x squared plus 4. If I plug in the opposite y value, then those should be the same equation. The same x values should come out of that. Well, it's not going to happen because even if I solve this for x, I get y minus 4, y minus the 4, take the square root, equals to x. But when I square root both sides, I get plus or minus. So they're not identical because I don't have the minus. The parabola that we're talking about, the actual picture, you could have done this too and said, well, it's shifted up 4. It's a parabola that looks like that. It's obvious it has symmetry on the y-axis. But I don't have symmetry along the x-axis because I don't have any portion down here like this picture said I would have to have. So it's no are on the x-axis. Okay, let's do the same thing. This is set up to check for the symmetry on the x-axis first since you solve for x. So that picture, no matter what it looked like, would have to be a duplicate image down here. Okay, and see, let me check the y. With the y being positive, that's x equals a positive y squared minus 3. And when you square a positive y squared, it still gives you x equals y squared minus 3. If I check the negative y, that would look like this. X equals to a negative y squared plus 3, which turns out to be exactly the same equation. That means when I use the negative y and the y, I got the same x values, meaning I plug in the negative y and the positive y, I have the same x value. So yes on the x-axis. Let's check the y-axis. That means you have the regular x, that's the original problem. Now, what if x became negative? Negative x, is that identical? Well, you should be able to say to yourself, no, it's not, because if I solve this for x, will it come back to the original? So I divide everything by a negative, x equals to a negative y squared plus 3. Is this the same as this? No, you can even tell just by the minus 3 and the plus 3. Forget that there's a minus here and a plus here. So it's no on the y-axis. No symmetry on the y-axis. This is a picture of a circle. We've had this before. I don't even have to do any work to realize that if it's centered at 0, 0, and the radius is 4, then does it have symmetry on the y-axis? Well, sure does. This is a duplicate image over here. Does it have symmetry on the x-axis without any work? This is a reflection of underneath the x-axis. So it has symmetry on x and y axes. Think about what happened. Just think about what happened. If x got replaced with the negative x, the negative cancels out, giving you the same problem. If y got replaced with a negative y, because it's being squared, it also will go away. So even algebraically, it makes sense, all right? This is an equation of a line. You should recognize that as an equation of a line. Let me just solve this for y just so you can see it. If I move the x over, then y equals a negative 2x plus 4. Most lines do not have symmetry with either axis. Most lines do not have symmetry. And take a look at the picture. The slope is a negative 2, and the y-intercept is 4. That's my y-intercept. Slope is 2, up 2 over 1, up 2 over 1. That line looks something like that. You can tell off the bat that it doesn't have symmetry on the y-axis. It's not reflected image. And it doesn't seem to have symmetry the x. But let's prove it analytically. To check symmetry on the y, make the x negative. Does it turn into the same equation? Obviously not, because now my slope is opposite of a over b is 2. I think I graphed this one wrong too, by the way, didn't I? Yeah, that should have been a negative slope. Oh, yeah, it is negative. Why did I go that way? It doesn't change my thought, but somebody out there is probably yelling at me saying, you didn't do the right slope when you graphed it. There. Okay, now all is well in the force. It was a negative slope. Now it's a positive slope. Either way, even if I still say, is there symmetry off of this? No, because that would have to be a reflection like that. Is there symmetry on the y-axis? Well, no, because if this thing is going this way, then I would have to see a reflection that went like this. And I don't. So if I check the y to be negative, 2x plus a negative y equals to 4. Same situation happens. Opposite of a over b still gives you this time it gives you a positive slope again. This is positive slope, and the original had a negative slope. All right, enough of that. The graph of an equation is symmetric with respect to the origin if the replacement of both x and y retain their result the same time results in an equivalent equation. I want to say same equation, but they didn't use the word the. The same equation. I wanted to say that. They didn't use the word the, so it has to, when you use the word an, then it has to start with a vowel, so equivalent. All right, let's see, he wants to check for origin. That means if I plug in both x gets a negative x and the y gets a negative y, then negative x squared plus a negative y squared. Does it give me the same equation? Equivalent is a tricky thing. It can look, the equation can look different, but it's an equivalent equation. In this, I'm not going to go into any detail. I think for the most part, you'll see that this still stays x squared plus y squared is 16. Not only is it an equivalent equation, it is the same equation. So yes, on the origin, there is symmetry. This one here, y is x squared, x cubed. Do you know what that means? That looks like? We've graphed that before. We graphed that before. It comes up, cuts over, keeps going up. That's the cubic. So if I say x becomes a negative x and y becomes a negative y, that's what happens. Negative y equals a negative x cubed. That still stays a negative y. And the negative times negative is still negative x cubed. Divide both sides by negative, you get y is x cubed. It's the same equation. Remember what we said before? That if we rotate this, I push this over, this piece is going to line up with this piece once it keeps going. It rotates around the origin, so it has symmetry on the origin. Origin symmetry. Okay, reflect. Is the graph that is symmetric with both respect to both x and y axes automatically symmetric with respect to the origin? No, because this one does not have symmetry of either x or y. This one only has symmetry on the origin. Now, the circle, on the other hand, does have symmetry about the x and about the y. So that was not a condition, so that's not true. I almost wanted to say it's true, but it's not. It's a trick. It's not really the true thing. I guess it could be how you're looking at it. This had symmetry with both. Therefore, it did have symmetry with the origin. If they're saying, if it has symmetry on both, will it automatically be symmetrical with the origin? Yes. But just because it is symmetrical with the origin doesn't mean it has symmetry to both. So is the graph that with both x and y is automatically, okay, this answer is yes. Is the graph with symmetric with respect to the origin automatically symmetric with, no, that answer is no. There's two questions there, okay. So I was answering the second question. The first question is a yes, that if it is both, it has to be origin. But just because it's origin doesn't mean it has to be both. We got a chart. You know, we love charts, don't we? We just love them to death. So this is a picture of an ellipse. And this has symmetry, obviously, the x-axis. So the equation is unchanged if, okay, if the y is replaced with a negative y, we get the same x. That's what they're saying. If a y, let me use a color here. If a y is replaced with a negative y, we have the same x value. That's symmetry on the x-axis. This one, if an x is replaced with a negative x, and x is replaced with the opposite of that, we get the same y value. That means it's symmetric on the y-axis. Origin, x is replaced with the negative x, and y is replaced with the negative y. We have symmetry to the origin, because we get the same equation back again. A graph is symmetric with respect to the blank, comma blank does not represent a function. Okay, look at those pictures. The only one that is not a function is the one that has symmetry with the x-axis. It's not a function, because the x value is used twice to get these two different y values. That's what they're asking here. Okay. Determine whether these are even, odd, or neither. Remember, even function meant was symmetry to the y-axis. Odd means symmetry to the origin. So you want to, I know you want to jump from x to the y. You want to say if this is y-axis, this must be x-axis, but it's not. The odd function is symmetry to the origin. A lot of people do mess up. So he wants to check what kind of symmetry, obviously, is neither even, so it doesn't have symmetry. If it just has symmetry on the x-axis, it would be neither, okay? Or have no symmetry at all. Determine whether these are defined as even, odd, or neither. Well, let's check for even first. We check for even, x has to become a negative x, and see if it changes the function. The question is, does f of negative x, does it still equal f of x? That's 8 negative x to the fourth minus 3 negative x squared plus 1. When you have a negative times negative times a negative times a negative, it becomes positive. When you have a negative times a negative, it becomes positive. Are they equal? This is the question. Are they equal? That's identical. So it is even. I don't have to check anything else. Well, I guess I better check if I do both. Let's check for origin. Because is it possible to have symmetry on the y and still have the on the origin? That means y would have to become a negative y. Let's see, if I randomly call this is my y, if I say is negative y the same as 8x to the fourth minus 3x squared plus 1, to get rid of that negative and solve for y is negative 8x to the fourth plus 3x squared minus 1. Are they the same as the original? No. So it's just an even function. All right, B. I'm going to try the even again. Let me see if what negative x gives me. Gives me 6 negative x cubed minus 9 times negative x. When you negative times a negative times a negative is still negative, so that becomes a negative. Sorry, I had somebody come in the room. All right, negative x, and that negative 6, that turns into a negative x. Well, I shouldn't do it right like that. me back up. It should still be that negative times negative is the negative 6x cubed. And then that gives me a plus 9x. Is this identical to f of x? No. So we know it's not even. Well, therefore, if it's not even, it can't be an odd function, because odd function, I have to be able to put the negative x and the y. Let's see. Let me do them both negative. Let's see. Negative y, is it equal to a 6 times negative x cubed minus 9 times negative x? So I know it's not even. It's not even. But let's see, I'm checking for, is it odd? That means both negatives go on the y and the x's. Negative y equals, again, negative x cubed plus 9x. But if I divide everything by a negative to solve for y, I get 6x cubed minus 9x. It's the same as the original. So yes, it's an odd function. It wasn't so bad, was it? Didn't kill us. Not much, at least. All right, let's do C. Again, I'm going to check to see f of negative x. This is how I check for my even function. Let's see what I get. 3 times negative x squared plus 5 times the negative x gives me negative times negative is a positive, so the negative goes away. 3x squared minus 5x. Is that the same as the original? Is that the same as that? No, it's not. It's close, but it has a minus 5. That one does not. So it's not. So then I check for plugging both of them and see what happens. Negative y equals to a 3 negative x squared plus 5 times negative x gives me negative y equals to a still positive 3x squared, still minus 5x. Get rid of that negative. Y now equals negative 3x squared plus 5x. Well, this part fixed, but now the first part's negative. So it's not on the origin, so it's not odd. So we call this one neither. It happens. Okay. Let's see, filling in the gaps now. If a function is defined by a polynomial in x, has only even components on x, including the case of a constant with x to the 0, true. X to the 0 means just a number. If I say 5x to the 0, it means 5. Is understood to have the even exponents. Understood to have the, I guess he's using the word even. I don't really like filling in his blanks. Even exponent. Blank will always be an even function. I don't know what he has here. Similarly, if only odd exponents appear in x function, will be, if there's only odd exponents, well then it should be an odd function. That would make sense. Translating. Okay, back to moving our functions around. The whole point of this lesson was techniques of graphing. The author must have felt like it was important to talk about even and odd functions that could help you graph. And yes, there's a little bit of truth to that, but most of us don't think about it. Okay, how do I graph this real quick? The parent. The parent is y is absolute value of x. We know what it looks like. 0, 0, 3, 3, 10, 10, negative 3, 3, negative 10, 10. We already know this. We should know this one like the back of our hand. How does it move? It has a number on the outside. That tells us that it's not left and right movement, it's up or down. It goes down 4. So all I'm going to do is every one of these points move down 4. 1, 2, 3, 4. 1, 2, 3, 4. In other words, I'm taking 4 away from every y value. 1, 2, 3, 4. The vertex. 1, 2, 3, 4. 1, 2, 3, 4. And there's my new graph. I missed it, but close enough. It moves down 4. That's all. It moved down 4. That's what happened. Okay. How does the graph compare to the parent? Moved down 4 units. That's it. So that's what that number did. Sure. Every y value went down 4. Every y value 1, 2, 3, 4. Every y value. So C tells us for every point x, y on the graph F, there'll be a corresponding point x, comma, y plus C. In other words, in my case, C was a negative 4. So therefore, y minus 4 is what I just did. If you go back to down 4. The graph of G will be the same as the graph of F, but translated C units up if C is positive, and the absolute value of C units will be down if C is negative. The graph of G is a vertical. I'm just guessing at his words. Translation. It slides. It slides down. That's what translation means. Horizontally was when the number was inside. We've had this already. Opposite of minus 4 means to the right 4. So the parent again, same parent. Same parent, 4 goes to 4. Negative 5 went to 5. Negative 10 still goes in. That's still the same parent. Still the same parent. But every value has to go to the right 4. So all my x comma y becomes, in this case, x plus 4 comma y. Every x has to move to the right, which means every x value, 1, 2, 3, 4, moves. 1, 2, 3, 4, moves. Even the vertex, 1, 2, 3, 4, 1, 2, 3, 4, and obviously 1, 2, 3, 4 would be out here. So there it is. We've already done these. I don't know why we're repeating them. Okay? When everything went to the right 4. Everything shifted 4 to the right. How did it? It shifted 4 to the right. And there it is. Given a function g defined by g of x equals f of x minus c, where c is a real number, for every point x, y in the graph of f, there'll be a corresponding point x, use a different color, x plus c, comma y. The reason I say plus is because it's always going to be the opposite of what you see. So if you see, well, I guess the g will be the same as graph shifted 4 units to the, if C is positive. If C is positive, that means you would see a minus, so that'd be right. If C is positive, just the C by itself is positive, it'd be right. But if C is negative, that negative makes it look positive, but really isn't. C is still negative. That's when it will go to the left, because if C is negative, you see negative C. You see that C is negative? We write it as plus, so that means we go left. F of x plus C, this thing is my parent. It's plus C, it must shift up C units. This must be shift down C units. This is inside the function, so we think opposite. In this case, C is actually a negative number, so we're actually shifting left C units. Even though it looks like it's positive, C is actually a negative. It's going to be a minus C. This one, think opposite. Shift right C units. Yes, you can put more than one transformation at the same time. Shifting more than one unit. So obviously, I'm going to go up 3. I'm going to go left 3, and I'm going to flip. This can get very complicated really fast. So I have to ask myself, which one should I do first? I'm going to move it first, then flip. Okay, so here's my parent. 0, 0, 5, 5, 10, 10, negative 5, 5, negative 10, 10. There's my parent. So if it's going to move, get a different color to show it moving left and up. Every point, left and up. Left 3, up 1. 1, 2, 3, up 1. There's my vertex. 1, 2, 3, up 1. 1, 2, 3, up 1. There's enough. There's enough for me to see what my left and right does. But now, remember what happens when we flip. I literally have to go upside down. So if you think about, this does get hard. If this is my bottom of my vertex, and I go 1, 2, 3, 4, 5 from the line, from that vertical line, then it's 1, 2, 3, 4, 5 down. So that point actually goes down to here. The vertex, you can't flip the vertex. It's going to stay there. The vertex still stays there, but this picture is going to wrap over, so it stays there. This point here, let's see, where was it at? It was, which point am I using? I'm just going to go here and say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Well, it makes sense. It should still be in the same. So there is my completed picture. And if you wanted to erase the evidence that you used to cheat with, that's your call. I'll do it just so you can, well, I can't get the right one. I want to cover up the evidence. That's what it would look like. It can get really, how can I put it? It can get really hairy fast. It's not the easiest thing in the world. All right, next problem. Is there another one on this page? There is. All right. This one might be easier because it doesn't flip. Okay, this inside here, I think you've got to be very careful with it. That 2 is affecting how fat or skinny it is. You just don't see it. You might want to realize this is, if I pull out the 2, it's the absolute value of 2 times x minus 2, if you think about it. Absolute value of 2 is just a 2. So it'll never be negative 2, and you still have the x minus 2. So you still have this absolute value parent. It's going to be getting a vertical vertical stretch. So let's graph the parent again. It's nothing different than it was before. It hasn't changed. It's the same parent. They keep, because it doesn't matter what the parent is. It could be a quadratic, it could be a cubic, same idea. The only difference is now is it has to shift to the right 2. So every one of these goes to the right 2, so let me do that first. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So this is what the shifting gave me. Okay, so I no longer have this. I no longer have that. Okay, but this has to now, every y value has to double because it is a vertical stretch. Every y value, if this is my y value, is being multiplied by 2. So what I'm going to do is this, to make it easy. 0 times 2 is still 0. 0 times 5 is now 10. So this point here stretches to 10. It's the same x value. This was a height of 3. It now becomes a height of a 6. So the vertex stays there. There is my new function. You can see how it's a vertical stretch of 2. Or you could even say it's a horizontal compression. Is that what they were calling it? Or no, they were calling it a shrink. Horizontal shrink of 2, because you can see how it shrunk in horizontally. So you have 2 different ways of looking at it. Okay? I would ask you if there's any questions, but you're just not here to tell me. So I hope that's what it does. You'll let me know if I'm wrong. Okay. We have a parent that is going to shift up 4 based on this after you shrink it. After you do this is going to cause it to be a vertical shrink. It's going to cut in half. Every y value cuts in half. And then there's a flip. So it does get kind of complicated which order we do. Now, that vertical shrink caused it to get fatter. So let me figure out what the vertex is going to be when the x value doesn't change. So if I make a table and I say, well, what happens when x is 0? Because I know that the vertex doesn't go left or right, because nothing's happening with the x. It's just being squared. So there's no plus or minus. 0 squared is still 0, times the negative half is still 0, plus 4. 0, 4 is where your new vertex is going to go. Well, before I say new vertex, let's do what the original parent looks like. The original parent starts at 0, 0, 1, 1, 3, 9, negative 3, 9. So there's my parent. But my new function, obviously that vertex is moving up 4. Okay? So it moved up 4 because of plus 4. And it is going to flip upside down, so I know it's going to do this. The point is, how do I know what it's going to do? Well, if I check for x is 2, and I take 2 squared is 4. So negative 1/2 of 4 plus 4 gives me a negative 2 plus 4. That automatically goes up to a 2. 2, 2. Should be on the graph. So 2, 2 is here. And if I do the exact same thing for a negative 2, since you're squaring it, it's also going to be a 4. Half of 4 is 2. Negative 2 plus 4, it's still the same answer, 2. So now I have my picture. There it is. And you can see that it flipped upside down. It helps to know what the vertex does, and that if it's going to flip, then you know I'm looking for the picture to be flipped going that way, and that's what I did to make my life easier. Okay, number 9, graphing translations and reflections. A function is defined. This is a picture of a function. How would it look if it was the same function added 3? That just means up 3. So every one of these points you see has to go up 3. That's all. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. I'm going to do it here only because I don't want to, well, I'll put it over there in a minute. It's going to go up here, it's going to go here, it's going to go down to, looks like it's doing here, then here. There it is. If you really, really, really wanted those points, that was a negative 4, 3, which makes sense. If it was at a 0, 0 plus 3 would be a negative 4, 3. So negative 4, 1, 2, 3. And if the other x was 0, 0 plus 3 gives you 3. That went up here. What about the one in the middle? It went up as high as, that was a negative 2, and it went up to 2, so it should go up 5. Because we're only adding 3 to every y value. This was down to a negative 4 when x was a 1. Goes up 3, 1, 2, 3. It goes to negative 1, negative 1. There's a lot of ways to do it. And then this was at a 0 height, so now at 3, 0 becomes 3, 3. And go ahead, just do your best to try to make your picture. It's a different scale. The grid's a different scale, so that looks actually bigger than this picture. This looks bigger than this one. What happens when you're adding 3 inside the function? Opposite, think opposite, left 3. So that means every x value goes left 3, but the y's stay the same. So negative 4 take away 3 is a negative 7. And I'm still going to stay at 0. This x was a negative 2, take away 3, be a negative 5. And how high do I go? I still go to a 2. Negative 5, 2. This was 0, 0, so it becomes negative 3, 0. See how I'm doing it? I'm just taking 3 away from the x. This was at an x of a 1. I'm sorry, x is a 2. So, was it a 2? It was a 1. 1, 2, 3 goes to the negative 1, but it stays down there at negative 4. Negative 1, negative 4. And the last part was the x is a 3, take away 3, goes to the 0. So do your sketch. The heights didn't change. It just changed what was happening here. Okay, that was fun. List all those points that I had originally. There was a negative 4, 0, and a negative 2, 2, and 0, 0, and a negative 1, negative 4, and 3, 0. Okay, for letter C, we have 2 transformations. Inside, that would be a right 2. Outside, that would be an up 3. So in essence, every x value adds 2. Every y value adds 3. So what I did was I put all the original points that we had in the graph, and I'm going to transform them. This should turn into a negative 2, 3. This should turn into a 0, 5. This should turn into a 2, 3. So I'm adding 2, adding 3. Adding 2 should be a 3, negative 1. And this one should turn into 5, 3. Let's cross our fingers to see what it looks like. Negative 2, 3 is here. 0, 5 is here. 2, 3 is here. 3, negative 1 is here. And 5, 3 is here. Let's see if it works. Different color here. Let's see. There's that little circular part. There's that part that goes down. And there's what goes up there. 2 transformations. Okay. What happens if all I do is flip all the y values? So the original points are still in black. So my new points ought to be, the new points should just be the same x value, but the y's should turn negative. So negative 4 should still be 0. Negative 2 now is a negative 2 because that flips. 0, 0 should still stay the same because you can't multiply this. Well, you can. A negative 1 times 0 is still 0. 1, positive 4, 3, 0 again. Let's see what that looks like. Negative 4, 0. I need a pen. Negative 4, 0 is here. Negative 2, 2 is here. 0, 0 is here. 1, 4 is here. 3, 6 is here. Oops. Something's not right. Oh, it's not 3, 6. It's 3, 0. Come on. Be my best friend. Thank you. That was, because it was a 0. Yeah, it was a 0, and so it's 3, still stays 3, 0. Okay, so this time the circular part went down here, then it kind of went here, and then it kind of went here. There you go. Close enough. So 2 transformations. This just went up units And, well, no, he wanted to put me k units up. This went k units down because there's a negative. This went h units to the left because there's a plus in there. This is h units to the right because there's a minus there. This has an A, so it's a vertical stretch if the graph of y equals f of x and A is greater than 1. Okay, it's a vertical stretch if it's greater than 1. It's a vertical shrink or a compression or gets fatter, whatever you want to say. This A is inside. You saw how I factored it out. It does the same thing. It is still a vertical stretch if the graph of y equals f of x and A is between 0 and, oh wait, no, between 0 and 1. That would, okay, now that would be, I don't know if he wanted me to call it a shrink. I will, because it's true. He tricked me, he flipped it around. If A is between 0 and 1, it's a vertical shrink. Or it is a vertical stretch if A is greater than 1. If you put a negative in front, it is a flip across the x-axis. If the y is inside, that negative's inside, then it flips across the y-axis. He didn't give us any of those, though. He didn't. He should have. Flips across the y-axis because the x's became negative now, so it flips over. And that's it. Now I'll be able to do this with you guys. So I'm going to save this and post it for you.